So let me start by introducing. So welcome everyone. Today's speaker is Brian Metzger, and thank you very much, Brian, for joining us. Brian, of course, needs no introduction in this community. Brian is a theoretical high-energy astrophysicist. His research is pretty diverse and touches on many topics: gamma ray bursts, supernovae, fast radio bursts, accretion processes, compact objects, astrophysical generation, nucleosynthesis, as well as the study of corresponding electromagnetic radiation from gravitational wave sources. Brian received his PhD from UC Berkeley before winning several prestigious fellowships, NASA Hubble Fellowship, the Lyman Spitzer Fellowship in Princeton, and then he was a NASA Einstein Fellow at Princeton. And then he joined the Columbia Physics faculty in 2013. Brian's work has been recognized by several awards. He received the Alfred Sloan Fellowship, the New Horizons Breakthrough Prize in Physics, the Bruno Rossi Prize, and just to name a few. And then recently in 2020, he was named the Blavatnik National Laureate in National Sciences and Engineering. So thank you, Brian, and welcome, and let's get started. And I think what we'll do is we'll go through, unless there are pressing questions, we'll just go through your talk and then take questions at the end.
Sure, and feel, you know, if there's issues of clarification, I'm happy to stop. I am going to minimize the movies of you, so I won't be able to see questions directly, but I am going to get started. So it's a pleasure to be here. I'm going to talk about multi-messenger signatures of neutron star mergers. I'm mainly going to talk about electromagnetic signatures. I have a longer version of this talk where, you know, I say some things about neutrinos. I haven't done as much on that. But I think what I talk about will be relevant to many topics, cosmic rays. And I'm going to come at it from the angle of the side of nucleosynthesis and trying to understand the origin of the heavy elements, because I think that's what motivated me in this field. And now it's sort of created a nice synthesis between the gravitational wave communities, the nuclear physics communities, and those studying high energy processes electromagnetically. And so I think that's a nice way to connect it, but there are multiple ways you could come at this problem, but that's going to be the focus I'm going to make. Oops, let me try to advance. Okay. So yeah, one of the motivations that got me started in this field is if you went back to the mid 2000s and asked, where do the elements from the periodic table come from astrophysically? The sort of standard picture looks something like this. Of course, hydrogen and helium are arising from the Big Bang. The intermediate mass elements are coming from massive stars, either their winds or when they explode a supernova for the most part. But as we got to the bottom of the periodic table, particularly elements heavier than iron, those that are produced through the rapid neutron capture process, which is about half of those elements, we're still sort of debating their origin. In this view graph, it says they come from supernova. We didn't know that was true. Some of them may still come from supernova, but our picture of this is obviously changing, but this includes many of the precious metals and transuranic elements. We don't know astrophysically where these are coming from. And so that's one of the motivating things. And it's actually an old problem of how you turn a relatively common element like iron into gold, one of alchemy. And you know, it's the difficulty is twofold. One is overcoming the Coulomb barrier as you get to very heavy elements requires increasingly high temperatures and densities, and those conditions are just not achieved inside of stars. And the other is the fact that, you know, if you look at a gold nucleus, it has many more neutrons than protons, and these are sort of coupled things. So in practice, in fact, it's actually easy to turn iron and gold. What you do is you just bombard an iron nucleus at a very high rate with neutrons, and this overcomes the Coulomb barrier. You can form a very heavy radioactive isotope, which then may decay back into gold. But then the challenge becomes, where do you get a very high flux of neutrons, a very high density of neutrons? Because in a vacuum, neutrons are, of course, unstable and decay into protons. So we need some kind of explosive hot environment, which involves a very high flux of neutrons if we want to turn iron into gold. And there are many types of sites for our process that have been discussed over the years. The popular ones in the 90s and 2000s were these winds that emanate from the newly formed neutron stars following successful supernova explosions. But as studies sort of improved in that direction, it was found that these winds that are driven off of newly formed neutron stars aren't quite neutron rich enough. Essentially, the neutron star is a very strong source of neutrinos, and the neutrinos and electron neutrinos and antineutrinos tend to equilibrate the neutron to proton ratio in the outflows, so that the even though the neutron star surface is neutron rich, by the time you get to the radii where the R process would take place, the outflows are not so neutron rich because of the strong irradiation of these outflows by neutrinos. And so I cut my teeth in this field by starting, thinking of ways we could modify this picture to make a successful R process. So for instance, making the neutron star very highly magnetized and rapidly spinning, so you could fling matter off of the surface so quickly that it would stay neutron rich and you could produce an R process in these winds. And this is the basis for these magnetorotational supernova channel that's been discussed in recent years, a sort of exotic type of very energetic supernova that might produce our process. The other one that's been around for a while is the idea of neutron star mergers. I think it was sort of considered fairly exotic and was not studied in as much detail. But as I'll talk about, we have direct evidence now that these mergers do produce these heavy elements. And then I think there are actually very similar physics that occurs in the accretion disks that may form in long gamma ray bursts. And so we should also take the progenitors of long gamma ray bursts seriously as possible R process sites. But I'm going to focus mostly in this talk on the neutron star mergers, because that's where we've had the most recent success. And I think we're all quite aware that in August 2017, LIGO detected this first neutron star merger. Not its only one, but it's been the only one we've had electromagnetic counterpart thus far. One of the interesting things to me was the fact that LIGO was actually able to measure the total mass of the binary quite well. It was around 2.7 solar masses. And this is actually in the middle of the distribution of galactic binary neutron stars. And so this event may be in some sense, representative of many neutron star mergers. Of course, LIGO also detected a more massive neutron star merger, which may have produced a qualitatively different outcome. But at least, this event for all purposes seemed kind of vanilla in terms of the properties we would have expected going in. But we do expect that there will be some diversity in the outcome of these events depending on the mass of the binary. More massive neutron stars, it turns out, will collapse to black holes faster than less massive ones. Very low mass binaries may produce remnants that never collapse into black holes. So there's a lot of potential diversity, but I'm going to focus on the canonical example that this event has provided for us. So I think we're also aware of what happened on August 17th. So about 2 seconds after the merger, there was a burst of gamma rays detected by Fermi-Lat. It was also detected by Integral satellite, which localized the gravitational wave event to this part of the sky. A few hours later, LIGO released its error regions and localized it to this region. And then there was some information from Virgo that further localized it. And so the source was localized to about 30 square degrees. And from the ground, astronomers looked at, various groups looked at all these different galaxies, and they found the fading kilonova counterpart in this galaxy NGC 4993 at about 40 megaparsecs. So strikingly close. This event was extremely lucky. Probably mergers this close are once in a decade events would be my guess. And what did they see? Well, they saw this fading optical ultraviolet counterpart, which was unlike any stellar explosion we'd seen before. It evolved much faster, had very unusual properties, was very clearly associated with this event. And what I want to talk, and once we had the optical localization, then we were able to point sensitive X-ray and radio telescopes and detect the afterglow, which actually took a few days to be produced, the afterglow from the jet. So I'm going to go through now some of the different processes that happen these mergers and the types of counterparts they produce. So I'm going to do this by showing you first a simulation of two merging neutron stars. This is a numerical relativity simulation, not my own work, but you're seeing the final few orbits of the two stars before they come into contact. You'll see strong tidal squeezing of the stars, the ejection of matter out of the outer Lagrange point of the binary. When the two stars actually collide, they produce a hot remnant which starts to oscillate, and the oscillation of this remnant produces some shock heated material that actually expands in all directions. So you have tidal material which comes out in the equator, but then you have a cloud of debris that actually moves out in all directions. You form a central remnant which is rapidly spinning, but eventually succumbs to gravity and collapses into a black hole, but it has substantial angular momentum, so you end up with a torus surrounding the newly formed black hole. And we think that the electromagnetic counterparts we see from these events are a very sensitive function of our viewing angle with respect to the angular momentum axis of the binary. So the idea has been around for a long time that the accretion of this torus onto the black hole could power a transient relativistic jet lasting a few seconds. And this is, I think Andrei Belobrodov a few weeks ago talked about how in this jet there may be different sources of internal dissipation, which lead to particle heating, and ultimately the production of gamma rays. But we think because of the bulk motion of that material in the core of the jet, that this brightest gamma ray emission is restricted to viewing angles within about a tenth of a radian or so of the axis. And for this particular event, we were viewing it substantially off of the core of what we think gamma ray burst jet would be. But as we're also aware, we nevertheless saw a burst of gamma rays that were delayed by about 2 seconds with respect to the end of the in-spiral. And there's a lot of questions about this gamma ray emission. Why was it delayed by 2 seconds? Why was it so less luminous than gamma ray bursts that we've seen at cosmological distances? So I think there's various reasons it could have been delayed by 2 seconds. One of them is it could have taken a while to form the relativistic jet. We think maybe a black hole may be necessary to get sufficiently relativistic material, and that could have taken some time. Another effect is that the jet has to actually break out of this cloud of debris that's produced during the merger, and the cloud itself is expanding almost at the speed of light. So the jet's kind of chasing the cloud, and by the time it breaks out, there can be a substantial delay. So it's not too surprising that gamma rays were delayed. There's also the question of why these gamma rays were unusual. We think this is possibly a different physical mechanism that produced these gamma rays than what we see when we view the events on axis. It may have been more akin to the shock breakout emission from the jet as it was breaking out of this material. Either the shock breakout of the jet itself, or, as I'll talk about if I have time, a magnetar wind that came from this remnant. But in any case, we do think we can't get a lot of information directly from these gamma rays, whether if we had viewed this on axis, it would look like a traditional gamma ray burst. We did have evidence for that there was a powerful off-axis jet from the afterglow. So as the jet material goes on, interacts with the ISM, it produces radio synchrotron emission. For a normal gamma ray burst, you're in the core of the jet and you see this emission essentially immediately. But when you're off axis, you have to wait because it's beamed out of your line of sight. You have to wait essentially until the jet sweeps up enough material that it slows down, that now you're in its causal cone. And this actually took about 100 days for this event before we were seeing the peak of the core of the emission from the jet. But one thing this event taught us is actually even off axis, even before we were seeing the core of the jet, there was some material from the sides of the jet that was producing its own afterglow, some mildly relativistic material that was initially directed towards our line of sight. That was important to explaining this initial rise. And so we see that this jet clearly had an angular structure to it. And the popular model is that this was imparted by the jet breaking through the debris, creating, basically accelerating a significant fraction of the ejecta to mildly relativistic speeds. And this is often referred to as the cocoon. And so, what we learned by detailed modeling of this is that this event did produce, we think, a fairly powerful off-axis jet that was viewed about at the angle that was inferred from the gravitational waves, and it had an total energy, which was comparable to those of cosmological short gamma ray bursts. And so, this is not direct proof, but it's pretty compelling evidence that this event did produce a successful GRB if we had seen it on axis. So I'm going to come back to a little bit later to the afterglow possibly, but I mainly want to talk about the kilonova emission, which is the fairly isotropic, as opposed to the gamma ray burst jet, the relatively isotropic thermal emission that's produced by the radioactive decay of the neutron-rich ejecta from this event when it produces these heavy elements. And the key point here is that there are several sources of neutron-rich ejecta during these mergers. I showed you the simulation. There was this tidal material which is stripped off from the outer parts of the star. When the two stars collide, as I mentioned, the remnant is oscillating, and it produces this sort of shock-heated material that expands even into the polar directions. We refer to these two as the dynamical ejecta because they essentially come out first on the dynamical time of the final in-spiral, which is of order of milliseconds. There's not a whole lot of this dynamical ejecta. A typical value might be 1,000th of a solar mass, but it comes out with the highest velocity. So it's essentially the first stuff you see in some sense, unless the GRB jet breaks through it. And these are important because they're the first material that comes out, but they're not. We don't think now that the dynamical ejecta is the dominant source of mass ejection in these systems. We think it actually comes out slightly later from the accretion disk outflows, the accretion disk that formed around the black hole. There are powerful winds from these disks. The black hole doesn't eat all of the matter, and actually the mass of these outflows from the accretion disk, which take place over the course of seconds, can be quite a bit more mass. There's an additional source of ejecta, which is not discussed as much in the community, but I think is actually quite important. And that's the fact that after the merger, but prior to forming a black hole, the remnant, we think, will be very highly magnetized because of all of the shear energy dissipated during the merger process. And so it's very likely that the central remnant is what we would call a magnetar. And because of the high angular momentum of the binary, it's essentially rotating at breakup. So we have a sort of a millisecond magnetar in the center of the system until it collapses to a black hole. And the combination of neutrino heating, neutrino ablation of matter off the surface with the centrifugal effect can actually drive quite a bit of mass from this magnetar wind in the, say, 1/10 of a second or a second after the merger before it collapses to a black hole. And I actually think this magnetar wind may have been an important source of ejecta in this system that we saw from 170817, because it turns out that we end up inferring quite a bit more fast material than I think we would have guessed, fast radioactive material than we would have guessed from this dynamical ejecta from 170817. And my best guess is that there was a brief magnetar phase. So to get back to the point of the accretion disks, so in this context, the black holes are fussy eaters. So you're feeding a black hole, a 1/10 of a solar mass in a fraction of a second. The midplane of these disks can get very hot, so hot that neutrino cooling, emission of MEV neutrinos, is quite effective. And so the midplane of the disk is in some sense tightly bound to the black hole, but the upper regions, which have lower temperature and can't cool as effectively through neutrinos, they get heated by the turbulence due to the magnetorotational instability in these disks, but they have no source of cooling because they're in a low temperature region. The photons are completely irrelevant to cooling this region. It's so dense, they're trapped. So you get these thermally driven outflows. The coronal regions, if you will, of these disks are highly susceptible to thermally driven outflows because they can't really cool. And so what our calculations of this show, and various groups' calculations of this show doing MHD simulations, is that about 30% of the initial torus is actually not making into the black hole, but is unbound in an outflow. And so if you have a 1/10 of a solar mass torus, which is a pretty typical value, you can inject several hundredths of a solar mass in these outflows from the accretion disk. Again, over the time scale, the viscous time scale of these disks is, fraction of a second or a few seconds. And so in this material, it tends to have a lower speed. It's about 1/10 the speed of light. It gets a boost in its energy because the midplane of the disk is mostly free neutrons and protons, but as they cool, they recombine into alpha particles, and this injects some energy and gives the wind a bit more power, but it's still expanding at about 1/10 the speed of light or so. And this is, I think, the most important source of mass ejection in these systems as the post-merger accretion disk. So as this matter expands into space, whether it's the dynamical material or whether it's the magnetar wind material or whether it's the accretion disk outflows, it will undergo this rapid neutron capture process. So I didn't say this, but these disks are so dense that they're electron degenerate, and in conditions of high temperature and electron degeneracy, that drives the composition in the midplane to be very neutron rich. Even if these disks were not neutron rich originally, weak interactions drive the midplane to be neutron rich. And so the outflows also, there's the issue of how much neutrinos change this picture, but the outflows themselves also tend to have more neutrons than protons. And so what happens first is the matter expands and cools, and you form these heavy seed nuclei. Most of your protons get captured with some of your neutrons into these heavy seed nuclei through standard thermonuclear reactions. But then you have so many neutrons left over that don't have a home yet, but they begin to then be captured by these nuclei. And in this way, over the course of actually a second after the matter is ejected, you form these heavy radioactive isotopes. And so this is showing you the chart of the nucleides. This is proton number and neutron number. We're following a single fluid element as it decompresses from high densities and temperatures. Along the top, you're seeing a running accounting of the nuclear composition as a function of atomic mass number. And then this is showing you the abundances are the colors here. So the stable elements is going to be a stable valley of elements is along here. And in this diagram, a neutron capture moves you to the right and a beta decay moves you up to the left. And so our process is a situation where you're capturing neutrons faster than you can beta decay. And so instead of following the valley of stability, you move far onto the neutron-rich side of the valley of stability. So I'm actually going to run the simulation now, and you'll see how this cloud of seed nuclei very quickly through neutron captures and beta decays, moves its way up to these very heavy isotopes. And then after about a second or so, now we run out of neutrons, and then everything that's been produced, this wide range of nuclei, decays back to the stable valley over the course of hours and days and weeks and months. So the key point for the kilonova is that this matter, if it were expanding and not being heated by anything, it would cool adiabatically, and we would see very little emission. We might see something from the cocoon, but we would essentially see nothing after a few hours. But because of this radioactive heating that keeps the matter hot, keeps it glowing bright, so we can see this event far away. So this is showing you the total radioactive power per gram of the expanding material as a function of time after the merger. So if you had a single isotope like you have in an ordinary supernova, like a 1A supernova, like nickel 56, you get a constant heating followed by an exponential decay, then cobalt decaying. But here you have hundreds of isotopes. So the ones with short half-lives decay into longer half-lives, into longer half-lives. And when you add them in aggregate, you get more of a power law-like heating, which is going something like T to the minus 1.3. So it's actually similar to terrestrial nuclear waste in terms of its heating rate. And this was some of our first calculations of this, but I should say that this heating rate is sensitive to your assumptions about the nuclear physics off of the valley stability. And many of these properties, beta decay times, neutron capture times, nuclear masses, have not been measured yet in the laboratory. And so you have to assume a model for those, and that introduces some uncertainty in the radioactive heating rate. And I encourage you to see Jennifer Barnes' recent paper where she sort of explores this, but kind of at the factor of a few, maybe even up to a factor of 10, all right, we have some uncertainty in the radioactive heating, and that will translate into uncertainty in translating the luminosity of the kilonova into the amount of mass produced. But in any case, so you have this expanding ball of radioactive waste. Initially, the photons are trapped in it. Basically, the photon diffusion timescale is longer than the evolution time of the system. But then after about a day or so, you reach this critical time where the photons can now escape and carry away this thermal energy. And that depends on the mass and velocity of the material, as well as the opacity. I'll come to that in a second. And then the peak luminosity is essentially the amount of mass in your material at the times the radioactive heating rate at this peak time, which is about a day, is like right there. So you can estimate the time scale and luminosity of this event. And when we did this calculation using the radioactive heating for the first time, 2010, we found that for typical ejecta masses and velocities, that this might be, of order 10 to the 41, 10 to the 42 ergs per second. And so that was 1,000 times brighter than a nova. And so that's the origin of this term, kilonova. But essentially, it's rising initially because radiation is still diffusing out. And then at some point, it kind of latches onto the radioactive decay rate. And at some point, you also have to worry about how effective these products are thermalizing their energy, because the energy is coming out in beta decays and fission fragments and alpha decays. And so it's complicated. And Jenny talks about a lot of that in her papers as well. And so that was what we saw in 2017 was this fading afterglow. And actually, many of these original models worked quite well in explaining the bolometric luminosity, for instance, showing you here, just comparing this original model from our paper to the data that was obtained from that event. And so it was very clear to me that we were directly seeing the synthesis of these heavy elements in this particular merger. But as I said, actually working out how much mass was produced, what its velocity structure is, what is the composition is another issue. And there's some information imprinted, we think, in the composition basically related to the colors of the kilonova. And this kilonova that we observed started off extremely blue with a peak in the ultraviolet at early times, and then evolved to become very red over the course of a week. And the colors of the kilonova are essentially related to the opacity of the material in the ultraviolet and optical. So the opacity, the dominant source of opacity, are a forest of atomic absorption lines by these complex elements that are produced in the event. And what we've come to appreciate, thanks in large part to work by Dan Kaysen and collaborators, is that you have very different opacities if your ejecta just contains lighter R process elements, or whether it also contains the lanthanide and actinide elements, those on the very bottom of the periodic table. And this has to do with the simplicity or complexity of their atomic structure. So relatively simple element that's, say, half-filled D shell valence electrons has relatively few atomic transitions. I hate calling iron relatively simple, but in this context, it's relatively simple. And so you have a relatively low wavelength density of lines, and this results in a relatively low opacity. So if you have light R process elements, you tend to get more optical and UV light coming out. Whereas if you have these heavier ones, because they have these more complex F shell valence electrons, they're in a combinatorial way, there are many more transitions, a much higher density of lines and wavelength space, and the effective opacity that results from these absorption is significantly higher. And this pushes the spectral energy distribution it basically blocks out all the optical and UV and pushes it into the infrared. And so for this event, we actually saw both. We saw evidence potentially for lighter elements contributing to the early parts of the emission, and then heavier elements contributing later. And this is not so surprising, because we don't expect there to be one component of the ejecta in these mergers. We expect there to be velocity and angular stratification of the material. Many of the sources of ejecta which come out in the polar regions, like the shock heated material or the wind from a magnetar, these are strongly irradiated by neutrinos. Neutrinos tend to make the outflows less neutron rich and make it harder to produce these heaviest elements. Whereas the outflows from the tidal material or from the accretion disk winds, in the equator particularly, they tend to be more shielded from the neutrinos, and so that material tends to be more neutron rich. And so we think we're seeing some combination of these two in this event, of lighter R process elements and also the heavier ones. And when people have attempted to model this at various levels of sophistication, the conclusion is that we have a total R process mass of a few hundredths of a solar mass, with a range of velocities between at least 0.1 and 0.3 times the speed of light. So I'm not going to go into the details of this. I just want to say the first question you might ask is, are these important sources of the R process elements on Earth? So the estimate you can do is you can say, okay, well, prior to the formation of the sun, at what rate would we need to produce these elements in our galaxy to explain the abundances on the sun? And that rate is about 10 to the minus 6 solar masses of R process elements every year. We now know from LIGO the rate of binary neutron star mergers with some uncertainty. So you can translate that into a Milky Way rate, and then you can say, okay, how much mass would need to be produced per merger to explain the solar abundances? And that number is uncertain, but it's around 1/100th of a solar mass. And we think that this event produced a few hundredths of a solar mass. So naively, at least, it does seem like these mergers are producing enough of these elements to explain the abundances on Earth. But we don't know if they produce all of them. In fact, we also have, I think there's some problems as you go to low metallicity and understanding how metal poor stars are able to have these elements on their surface, given the delay time distribution of mergers. So my view is that there probably are multiple sources, but I think this event has confirmed to us that neutron star mergers are an important source, and it may be the dominant one at the current epoch in the evolution of our galaxy. So there's one way to test this, and that's by looking for the last neutron star merger remnant that actually occurred in the Milky Way. So as you may be aware, one way is we can go look for the radioactive decay from the isotopes that were produced in the most recent merger in our galaxy. And this has been done for massive stars with aluminum-26. So aluminum-26 has a half-life of 1 million years. Supernova happen every 100 years. So there's about 10 to the 4 supernova contributing to the aluminum-26 signal that we have thanks to COMPTEL and the galactic plane. And that tells us where the young and massive stars are. We'd like to maybe possibly do the same thing with neutron star mergers. So you can just go through the isotopes that are produced in the neutron star merger and look at their half-lives and look at their intensities and look whether these are common elements or rare elements and get a sense of what are going to be the most promising candidates. And many of them are just too short-lived or too rare in their abundances. But the one that sticks out as being promising, or the most promising, which is still not super promising, is aluminum-126. So it's near the second R process peak, so it's fairly abundant, and it has a half-life of a few 10 to the 5 years, which means there still might be a few remnants in our galaxy that are emitting this line. And so with Mengru Wu and Prajwal Banerjee and our Columbia collaborators, we did a Monte Carlo calculation, basically placing neutron star mergers around the galaxy and calculating, for instance, their tin-126 signal. So tin produces 3 lines and the several hundred keV range. And this is essentially a result. This is showing the photon flux on Earth. This is just a Monte Carlo realization. We don't actually know where the recent mergers happen. But given this half-life and given the fact that mergers happen roughly every 10 to the 4 years or a few by 10 to the 4 years, we think in the Milky Way, there should be of order 10 mergers that have appreciable gamma ray line fluxes. And the typical number one gets from this is around 10 to the minus 7 photons per centimeter squared per second. And this is going to be really hard to detect. To give you some example, this amigo concept that is being considered over a 5-year survey would only get to a sensitivity of 10 to the minus 6. And we also don't know where these mergers are actually, remnants are happening. So one thing that may help you is the fact that we do think some mergers will happen outside of the galactic plane. We have evidence for this from gamma ray bursts that they do happen outside their galaxy disks sometimes. So we may look for weird, at this phase, 10 to the 5 years after the event, it's past the set-off phase. It's starting to basically mix into the ISM. So you're not going to see a lot of difference between these events and a supernova remnant. But maybe if it happens outside of the plane or has some irregular morphology, it might be a promising contender. So in the future, we need to think about how to improve the line sensitivity if we want to perform this exercise. I'm running a little low on time, but I want to just point out that this was a remarkable event we had from 170817. Many of the signals that people thought we might see, this is from my 2012 paper with Ito, were in fact seen. We saw the gamma ray burst. We saw its afterglow, albeit an off-axis version. We saw the kilonova. There's two things that we might want to still see. One is the interaction of the kilonova ejecta with the interstellar medium, which might produce its own afterglow. And if we want to, accelerate cosmic rays that have this exotic composition, this is the shocks that we would be looking for. We also might want some evidence that the compact remnant actually formed a black hole in this event. I have many pieces of suggestive evidence that it did form a black hole. I could tell you about them, but we would like some clear-cut evidence that it actually did. And so I think we're starting to get hints in this direction from an exciting recent discovery. So as I mentioned, the afterglow after rising began to fade very quickly after 100 days, and it continued to fade until very recently. So about 3.5 years after the event, there was a very deep observation taken by Chandra, very deep integration. And to the surprise of our group, one of the groups working on this with Raf Maigrudi's group, it was still detected in X-rays, whereas the radio now has faded. And so this is telling us, actually, it's not obvious from this fact alone, but it's telling us that there's been a change in the spectral slope of the afterglow emission. For this whole phase, it essentially had a optically thin synchrotron spectrum, the single spectral index. And now, if this is really the case, it seems like it's gotten brighter, relatively speaking, in the X-rays than radio. So stated another way, if you look at the X-ray flux, this is sort of the afterglow model, the decaying afterglow model. In recent years, it seems like the X-ray flux has flattened considerably, and there's still a lot of uncertainty as to the calibration of this, but at least the claim in the paper that I was on is that this is about a 4 sigma excess over the best fit afterglow model. So we're getting hints that there may be an extra source of X-rays which is kicking in the system, which is not yet exhibiting a radio component. So there's 2 models that have been proposed for what, if this is real, for what is producing this excess X-rays. One is that we're for the first time seeing the kilonova afterglow. So we're first time seeing the kilonova ejecta interacting with the ISM. And the idea here is, remember, the fastest component of the kilonova is probably this dynamical, either the tidal material or the shock heated dynamical material. And so you have a small sort of tail of very high, this is the amount of mass above some gamma factor. So this is the non-relativistic mass, which was contributing to the kilonova, but then there's a tail to very high velocities. And depending on the numerical relativity simulation and what it assumes about the equation of state of the neutron star and how it handles the numerics, et cetera, you can get different predictions for whether this sort of tail of high velocity material. And different amounts of this high velocity material lead to sort of different predictions for when this kilonova afterglow will turn on and what its slope will be, et cetera, et cetera. So I will admit I was always a bit skeptical of the numerical relativity results trying to resolve a tiny bit of mass expanding at very high velocities? Are they really, resolving this tail properly? And so partly as a result of this, and actually in the context of something else, we worked with Rodrigo Fernandez at Alberta and his master's student Coleman Dean to perform simulations where we don't try to do the full in spiral in numerical relativity. We just try to do the very final stage where the two stars are colliding, but try to do it in hydro, but with really high resolution to see if we can get convergence with regards to this fastest ejected component. I don't want to talk about the details of this, but we actually, by going into the co-rotating frame of the binary, we actually get away with axisymmetry in the simulation, which saves us some computational time. We have to include the Coriolis force and the centrifugal force in this frame. But where we find that the fastest material expanding greater than 0.6 C is in fact converged with spatial resolution, that it's about 10 to the minus 5 solar masses. And so that sits about here on this earlier diagram. So it does seem like the grid-based hydro codes are getting close to resolving this fast material. So they may be trustworthy, we find. But in any case, So it's viable. This idea that maybe we're seeing the kilonova afterglow as this X-ray excess is certainly a viable possibility. It doesn't really explain why the spectral slope has changed, why the P index of the electrons has actually gotten smaller for a less relativistic shock. This may or may not be expected theoretically, but anyways, it remains viable. The other possibility for producing this X-ray excess is that we're beginning to see emission from the black hole remnant itself. So it takes about several years for the kilonova ejecta cloud to become transparent to the soft X-rays because it has an enormous bound-free opacity. But right about the current epoch, we should start to be seeing the central remnant potentially if it's accreting matter that is continuing to fall into the black hole at very late times. And so the question then becomes, is enough matter falling back to the black hole at these late times that we could see this signal? And there are a few interesting aspects of this. So the level of the X-ray excess is about 5 by 10 to the 38 ergs per second, which is similar to the Eddington luminosity of the black hole remnant we think should exist there. So before this phase, if there was fallback, it would be highly super Eddington, but it's now just becoming sub Eddington, which means that there may be, maybe there's a narrow beaming of the X-rays, but now it's starting to come into our line of sight. The ejecta is becoming transparent. And the other nice aspect is that if you calculate the thermal disk temperature at this luminosity, it's a few keV, which is right where Chandra is sensitive. So it makes sense that this would, if this is thermal emission or even non-thermal emission from the disk, it would kind of make sense that we would just be seeing this in the X-ray band. So we try, but the key uncertainty is whether there's enough matter that's coming back to the black hole 3 years after the event to explain this level of luminosity. So we looked at this with Rodrigo Fernandez. We ran some of our hydrodynamical simulations, alpha viscosity simulations of the accretion disk to very late times in the sense of 30 seconds after the merger, which is a million dynamical times at the ISCO. And we followed it in a big grid because we wanted to follow the very moderately bound matter that may be coming back to the black hole 8 times. And what we found is kind of interesting. So this is showing you a snapshot of the simulation. These are all at the same time, but this is sort of zoomed out. So this is near the black hole and then zooming out to scales of almost a solar radius. And the colors are showing you whether the matter is bound or unbound from the black hole. So red is unbound and blue is bound. And what we found was that the early phases of the disk evolution, when it's producing these powerful winds, you do produce a lot of unbound material, but you also create in the equatorial region a kind of bound cloud of debris. And that bound cloud continues to feed fallback matter into the inner disk, even to late times. So at these phases, 30 seconds, days after the event, weeks after the event, this matter that's falling back lands in the accretion disk. It's not able to cool. Very little of it actually makes it into the black hole horizon. Most of it is ejected in the wind, but the winds tend to come out in the polar regions, and they kind of come out in a different direction. And so this is showing you the fallback rate or the accretion rate as a function of time after the merger. And the red line is showing you the rate at which matter is falling from this cloud back into the inner disk, and the black line is showing you the rate the black hole is consuming that matter. So as I mentioned, at early times, the accretion rate is very high. The disk is able to cool efficiently through neutrinos, and a significant fraction of the matter falling back makes it into the black hole. But then after about a second, neutrino cooling shuts off, and now matter that's falling back doesn't make it into the black hole. So you get a divergence between the fallback rate and the black hole accretion rate. But if you extrapolate the fallback rate all the way to 3 years, now the fallback rate is becoming sub-Eddington, and so the disk can start to cool through photon emissions. And so we may expect the black hole rate, we're not actually simulating this, but we would expect maybe the black hole rate would rise again to meet the fallback rate. And if you extrapolate the fallback rate to 3 years, we get to, depending on the alpha viscosity we assume and the ability to extrapolate a simulation from 30 seconds to 3 years, we do find there might be enough matter coming back at these late times to explain the magnitude of the X-ray excess here. But also not overshoot the kilonova, because the reprocessed X-rays could enhance the kilonova emission. So we don't want to start making radiation efficient X-rays too quickly, but it turns out that it's okay. So I'm basically out of time. I'll just say 2 quick things. One is I've talked about a neutron star merger that collapses into a black hole. We think that's probably the case with 170817. It's possible, however, that the merger may produce a neutron star which doesn't collapse into a black hole for at least for many days or longer after the merger. And this can substantially change the picture, because now the kilonova is powered not just by radioactivity, but it can also be powered by the magnetic spin down power of the magnetar. And this may produce a luminosity in the X-ray and optical, which is qualitatively different than what we saw from this event. A much more powerful event, potentially. There's a lot of rotational energy in one of these magnetars before it collapses into a black hole, like 10 to the 53 ergs. So if you tap into some fraction of that energy, you could make a very different signal. And we actually are starting to get some hints from some gamma ray bursts that they may be producing too much optical emission compared to what we would expect for their kilonova signal. I don't have time to talk about this in great detail, but we're starting to monitor a lot of short gamma ray bursts at late times to try to look for the radio signal, the bright radio signal that would be produced if the magnetar was injecting significant rotational energy to the kilonova. So far, we mostly just have upper limits. But we'll continue that program to look for evidence that in some short GRBs, there might be long-lived magnetar remnants. So I'm just going to stop there and take people's questions. Thanks.
Thanks, Brian. Jules.
Yes. Hi, Brian. Speaking of late time X-ray events, there was another X-ray event that's not talked about very much in this same object. Near the peak of the X-ray emission at about 160 days, there was a paper about showing that it looked like there was a rapid increase in the X-rays, like a short flare that began around about day 150, near that peak, and that such a short rise was maybe evidence for some reactivation of the central engine. This is a paper by Piro, and I haven't seen much discussion of that beyond that paper itself, but it brings up some of the same points that you just made, which is that there could be a reactivation due to a central neutron star still being there, and also that it doesn't have to be powered entirely by, this neutron star doesn't have to continue to spin down entirely by electromagnetic radiation, but it could still be spinning down due to gravitational wave emission. And the electromagnetic power of that neutron star could be ordinary and not necessarily overproduce the X-rays, because it's still a rather low X-ray luminosity at that time. So what do you think that's possible?
Yeah. Well, yeah, I should say, I don't want to comment on observations. I know my colleagues are skeptical for some reason of that detection, but I don't work on that. So assuming it's real, I agree, it would be quite indicative. I don't know if I necessarily say it would have to be a neutron star. I mean, it could be that at 150 days, I mean, it would still be, if we're detecting it just barely, it's probably around Eddington. So I don't know, maybe there would be a way it could also be like a clump of matter that came back and, it excited the X-ray jet of the black hole too. So, but in terms of it being a neutron star, I think the main argument is, yeah, that you could, so you'd have to hide most of the rotational energy of the neutron star because we don't see it showing up. If you were injecting a significant amount of energy to the afterglow, we would start to see it in that event. So you have to be getting like 99% or well, either that or as you say, a very weak spin down of the neutron star, so there wasn't putting that much energy into the ejecta. And I think it's hard because the gravitational waves at these late times would be produced by a non-spherical like shape of the remnant, and the easiest way to do that is by having a strong magnetic field inside of the star.
Yes.
So you have a bit of, there's a bit of a fine, not fine tuning, but you have to put a strong enough field inside the star to distort it, but then
exactly.
not have an outside field so it doesn't spin down that much through the dipole. So I think it's possible. It's possible to do that, but I don't know if it's easy. So it's a fair point. But yeah, I think on basic grounds we do expect the interior fields from these mergers to be enormous, but there's a big uncertainty in translating that into the dipole field. So there is a way to suppress the dipole component, but have an enormous field inside, then that becomes a possibility. Yeah.
Well, Maxim Barkov has a question, but maybe Maxim, I'll just ask myself one very short question. Brian, could you comment the delay between the merger and the start of gamma ray burst? I mean, the main event. It's could be calculated, and if yes, what is the range? What is the interval expected between the merger and start of gamma ray burst?
Yeah, I haven't given this a lot of thought. I think it does. So there are two delays that could arise. One would be that the time between the merger and when you form the GRB jet, and the other could be the time the jet takes to come out of the cloud of the debris. And then the third time would be if you're far off axis, there's an additional delay time due to the light travel time when you come out of the cloud. So I think if you just consider the latter two, just breaking out of the cloud, I don't think we'd expect a huge difference between different events. So if that's the explanation, I would expect the delay to be, to maybe be a function getting longer a little bit further off axis, but not being terribly longer delayed. But if it's a matter of having to form the black hole, I mean, theoretically that delay could be significantly longer. The challenge is, while you still have a neutron star remnant, it's the region above the remnant is not clean. There's a neutrino driven wind that comes off of the remnant, which makes it really hard to form a GRB. So I would say, our expectation is that more massive neutron stars will immediately collapse into black holes. They undergo what we call a prompt collapse. And so we may see some that have a shorter delay from the more massive ones. But then, as Jules said, if you have a low mass one that makes a neutron star, we don't even know theoretically whether that's going to make an ultra relativistic jet for at least a few seconds. So So we could see significantly longer delay. So my best guess is most of them will be around this same delay time, because I think 72917 it's in the middle of the mass distribution or galaxy, so it may be a fairly canonical event. But we certainly could have a tail to much longer times, and maybe even much shorter ones. Like LIGO had this other merger 190425, which was significantly more massive and almost.
So these are seconds.
What's that? Would have almost certainly undergone a prompt collapse. So anyways, I think you could expect almost. There's probably going to be some minimum delay, which has to do with getting out of this cloud. But beyond that, I think you could have much longer delays. So, yeah.
So seconds typically.
Seconds. It could be, yes. It could be as long as seconds, I think, or yeah, or even longer. But if it gets longer, then it gets harder. You know, even if you make a jet, it's going to be lower luminosity probably. So it's going to be harder to, yeah, because this disk that's powering the jet can't hang around forever. So.
Why I'm asking a bit more practical reason, because the best gamma ray burst detectors are actually the Cherenkov telescopes. So if you could manage to go to low energies, that's a huge area. So there's a lot of possibilities. But there's one caveat there that they are just, you have to direct, and then typically we could miss always the main event. So you could go afterglow or early afterglow. So it would be great if this event could just tell us, give a trigger, not trigger, just to trigger and to observe. So seconds maybe is not so bad, but yes.
Yeah. I think it gets harder because you may wait longer, but then your disk might be gone. So when you do form a black hole, maybe it isn't as powerful of a jet. So there may be some trade-off in how long. If you have very long delayed events, how bright of bursts they make. So they could be dimmer bursts. But
okay, thanks, Maxim.
Hello, I have a question and comment. It's like, Brian, do you remember our paper with Editon, Dmitris, and Maxim Lutikov about a prediction of rebrightening of this event?
Prediction on what with regards? I'm not sure I remember this. So you were predicting that it would rebrighten because of a magnetron
in a year scale.
Okay,
we published it in 2018.
Okay, I was not aware of this. Okay, sorry. So what is the nature of the prediction? So why was it rebrightening?
The idea is very simple. You have like a first power law, afterglow. It's via off-axis, and we have like a cocoon interaction with intermediate surrounded media, and we have this power law like a fading structure. But jet can be quite relativistic, and we didn't see it so far. It starts to be sub-relativistic, starts to be seen from an angle like 20 to 30 degrees. And when it's slowed down, we start to see like a second bump with duration about like 1-2 years, with the same duration like.
So in your model, is it coming? So it's coming from the GRB jet. It's not coming from
yes.
a separate component of ejecta.
Yes.
Right. Something with it becoming sub-relativistic produces a second peak. I have to look at this. I apologize. I was not aware of your prediction. I have to understand.
I think this could be quite natural explanation.
Okay. Well, yeah. So maybe it's I mean, but would you predict a change? Because the other thing that's mysterious about the brightening is the fact that it doesn't seem to be, well, it's not brightening yet, but it's flattening. It seems to be getting harder, the spectrum. So is there any reason you would maybe get a change in the synchrotron spectral slope as well?
So because you have a different population of particles there.
Okay. And so you have a different acceleration index or something.
Yes.
Okay, I'll have to look. I'll take a look. I apologize for missing that.
Okay, so let's move to the next question. Jim Buckley.
Yeah, just a quick comment. If just in kind of sorting out the relative role of neutron star mergers versus, say, something associated with supernova remnants and contributing to the synthesis of the ultra heavy elements. There's an interesting thing I learned about from my cosmic ray colleagues, that if you look at the cosmic ray composition of the actinides, just the elemental composition, the curium and the plutonium are dominated by these kind of longer, from the standpoint of the lifetimes you showed, but these kind of intermediate hundreds, thousands of year kind of decay times of the unstable isotopes of curium and plutonium. So those dominate the elemental abundance. So by measuring the elemental abundance of curium and plutonium relative to thorium, you actually have kind of a razor or something where you can discriminate between these relatively rare neutron star merger events that must have happened so long ago that those elements would have decayed away, from relatively more frequent nearby supernova related explosions where they would still persist. So it's just a comment. I would like to know your reaction on this, because I've learned about this relatively recently and been thinking about it in connection with my own concept for a future gamma ray mission. But I mean, I think you have Poisson fluctuations too in the neutron star merger rate, but maybe there would be some other evidence of a recent neutron star merger where you could rule that out. I'm just wondering if you were aware of this, or.
Yeah, I'm aware of the isotope work, and then there's
this
also,
is not ice. Yeah, this is elemental though. I think just because the isotope dominates the elemental abundance. Sorry. You see what I mean? Like, so it's a simpler measurement.
Okay. Yeah. I am aware. I may not be aware of that specific argument. I am aware of the arguments about the fact that we have only like upper limits or very weak measurements of plutonium on the ocean floor, and how if they were supernova, we would expect there to be a sort of more persistent rain of plutonium doped grains into the earth, because we see iron 60 on the ocean floor, we don't see plutonium. And so I am aware that this has been used. There's a paper by Wallner and then also Hotekizaka where they look at this in the same context. Like if I had supernova, they would be very common. So I'd expect a sort of constant flux of these plutonium. But then if you look at something rare like a merger, you have to be in the right pocket of the galaxy, on the half-life to be able to see it. I think there are definitely a lot of, I wouldn't sell each of them individually, compelling arguments that are pointing towards the dominant R process site being rare. So one of them is the plutonium. The other is, if you look at dwarf galaxies, there are some extremely R process polluted stars in some dwarf galaxies, and some dwarf galaxies where there are no R process elements. And the argument has been that if it was as common as a supernova, you'd expect to be kind of see the same amount, but it looks like one galaxy happened to have one of these rare events and the other 9 out of 10 didn't. So this is work by Anna Freibel and Alex G. So yeah, I think there's a lot of hints that the dominant source is a high yield, low rate event, and this may be an additional contributor to that argument. But then that doesn't really answer the question, because the competing models now that are theoretically most promising either involve neutron star mergers, which satisfy that manifestly, or rare subtypes of supernova that may not be every core collapse, but maybe every 100. The one I've been interested in at low metallicity are collapsars, so the same rapidly rotating stars that give rise to long gamma ray bursts. These same accretion disks that I argued are happening in the mergers and producing these neutron-rich winds, those same accretion disks should exist in collapsars. But then the R process signature is more subtle, because you have to look for it in the core of a supernova where there's a lot of ordinary matter on the outside, and then you have to look for this sort of R process core in a collapsar. So anyways, I think your point is well taken, that and I would actually be interested if you'd forward me this study, because I do think there's a number of weak evidences that have been put forward. But that doesn't really solve the issue, because we don't know if there's a rare subset of supernova, which would be
right. A rare subset would give you the same result as neutron star merger.
Exactly.
And basically, this is a measurement that can't be made yet. I mean, it takes a much larger instrument, and it would just be, if you saw those elements, it would just mean that the neutron star merger or the rare supernova thing was disfavored, that it was a more common missed, or process chain or something. And so anyways, I just wanted to bring that up. So
I think one thing I would just say is it's important to address this question at different epochs in galactic history. So the dwarfs answer the question at low metallicity. Things like this may answer it at high metallicity or at current epoch, which is a different question. So yeah.
By the way, Brian, one question. What about our knowledge about nuclear reactions? I mean, all these codes have been developed, the decades ago, and they are successfully applied, like supernovae and others. So do you have a progress in this area, or you don't need any progress? Everything is
Oh, there definitely is progress. There's this FRIB facility for rare isotope beams that they're building at Michigan State, and this is actually measuring these quantities better to do these types of calculations as one of their main science cases. And there are similar facilities across.
Is it critical, or is just the same which we knew is?
Let me put it this way: Our simulations are not perfect, and we're folding them into a nuclear reaction network, which is not perfect. And then we're trying to reproduce a very detailed measurement like the abundances of the sun. So I probably should stop recording the thing, but I'm skeptical of the endeavor a little bit that we're going to solve the problem this way, because I think there will always exist cross sections we don't know, uncertainties in our simulations. The broader questions like whether a given amount of neutrons to protons gets you up to a certain element, like roughly, I think those are more robust. But if we're going to say, like, I want to produce the solar system R process like precisely, or metal stars R abundances precisely, I think this is really hard. I think there's a lot of things like fission fragment distributions of very, very heavy isotopes that will never be measured in the lab. It's impossible. So there are inputs to our code where we're always going to be relying on uncertain theoretical models. So there is progress. I'm not saying it's not improving, but it's hard.
Okay.
So I think, yeah, the goal should not be to produce exact agreement with observations.
Okay, thanks. Okay. Any other questions? Yeah, I don't see.
I should probably get going.
Yeah, and also I think yes.
Thank you, Brian.
Thank you, Brian. Just
yeah, thanks.
So as Reshmi indicated at the beginning, if you have some comments or some ideas in the context of this talk, we could continue a bit more. We have time. And for example, I interrupted Maxim in the sense that, he wanted to tell about his work, but not in the context of the questions. But now, Maxim, if you want, you could describe or you say a bit more about your work. I guess Maxim.
I'm here.
Yeah.
It's like it was simple prediction. What if we technically I described it already. It's we have like a standard setup. You have like a door which accreting. You have like this ejector, and when your jet comes through ejector, you form a structure like a jet, fast moving jet, plus spherical like cocoon emission. Like a jet break forms spherical shock with low like a Lorentz factor. But jet itself, after passing through cocoon, can keep moving very quickly. At least like what we see here, like it looks like we didn't see jet itself when in the main phase. It was like a two component gamma signal in a like hard X-ray soft gamma, and one of it looks like it's thermal emission, which is soft and long, and one is short breakout, not thermal. And very probable what we miss fast moving away jet itself. And this jet somehow, somewhere should slow down. And when it slows down, it should emit. It's a very simple logic. And probably what we see like rebrightening, it's just slow down, slower jet itself.
So this is an alternative explanation?
Yes.
What Brian was telling
Yes.
us?
Yeah.
But then
And interesting, what we put this idea in archive before rebrightening itself.
well, you of course will be biased, but nevertheless, if you compare these two explanations, I mean, you would say your explanation is better, of course, but but nevertheless, if you compare in unbiased way, so or you could distinguish between this observationally between these possibilities, or
Probably yes, because here it's quite
different life curves.
Yes, different life curves. Because in Brian's explanation, he has a very free parameter of transition of ADAF disk to Shakrov-Chunyayef disk, which is a little bit strange because of like disk starts to be thin and at lower accretion rates, and for like a high accretion rates about like a 10 Eddingtons, it's can be quite thin. It became thicker than usual, but if I remember correctly, it was not so trivial, so sharp phase change like in low accretion rates. So like here it could be quite discussable, quite tricky point, I would say.
But this is reduced to uncertainty of the accretion regime. I understand
Yes.
what you're saying, right?
Yeah.
So does it mean that then predictions could not be very robust in that case because we are, I mean, because of these uncertainties?
Yes. 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 Yeah.
Okay, I think we should not discuss too much this because I mean the authors, I mean the without Brian, so unfortunately he left already. So some other, I mean, comments, wishes.
Well, maybe one comment. For some reason, this hasn't been discussed here. I thought Brian was going to talk about it, but there was some evidence of superluminal motion from the radio emission that was seen. I mean, the whole situation was very confusing because well, we never knew if we were seeing a jet or if we were seeing something more isotropic. But the evidence for the superluminal motion seen around 60 days seemed to suggest that some of the emission was coming from a jet. So that's built on this picture that the early times might have been kilonova and the breakout, and then the jets taking over later on. Brian's picture is always clear. I think it's still quite confusing what's actually gone on and what we're actually seeing, if we're seeing the jet or not.
Can I answer that?
Yeah.
I think it's the superluminal motion tells us quite clearly that we are seeing now a core of a jet.
Of course. If that's a robust measurement, of course.
Why not? We have three different measurements.
Yeah, because it's also with how good your pointing is, of course, because you've got to have a reference. I mean, you know how tricky it is, especially when you've got a point source. So you have to, I mean, if it's robust, then you're right, but it's about being, you have to be doubtful, right?
I'm not sure. There are two different measurements by two different groups. One of them with the same facility, so it's not a absolute astrometry, it's relative astrometry. And so this is one thing. The second thing, which is unrelated to that, is that the shape of the peak and the decay of the afterglow after the peak is what you would expect from a core of a jet, and not from something which is more spherical. So there is a very different prediction for how the afterglow should behave after the peak. So everything.
Well, that's a bit tricky, right? Because what you're saying, particularly like how it's peaking. I mean, there's been this question of whether we're seeing. We know we're not just seeing a top hat Lorentz function. Lorentz factor distribution. That there's probably is as a function of angle as you come off axis. There's a whole distribution of Lorentz factors. Right, so these models have not been wonderfully predictive on the light curve, because you have to put in quite a lot of physics of how you think the Lorentz factors distributed. Again, this wasn't brought up at this discussion. But
no, not necessarily, because if you have a jet with structures that most of the energy is in the core, and there is less energy in the wings, then at the peak you see the core of the jet, and you don't care about the wings anymore. So the wings are dominating the rising phase, and the peak and decay are completely dominated by the core.
You know, I think another key measurement, which is a holy grail for like some of us experimentalists, is the polarization signatures that are involved with this. Like if you have decelerating regions in the jet, or maybe just one decelerating jet, and there's going to be a point at which you kind of view the kind of edge-on view when you hit the when your viewing angle hits the 1/gamma angle, and there'll be a very robust polarization flip. The problem is it's only like a couple percent or a few percent. So in the optical or in other bands, I think polarization signatures could disentangle some of these tricky geometry questions, but they'll probably get garbled as well. But I just wanted to.
Jim, on that front, what's the most promising band to be measuring this in with regards to that? Because we've only got limited sensitivity in some bands.
So many years ago, I actually did a calculation, but we didn't publish it with, he was a student, Ilya Zelkovich at the time. And we looked at what type of, in the optical, what would it take? And basically, what I can tell you from an experimentalist standpoint is in the optical, it would take kind of a 4-meter space-based telescope or something like that. So I haven't thought about it that much in the gamma ray regime, but I do know with New Compton telescopes like Amigo or my own kind of concept, which is a bigger instrument. I mean, I think you might just barely touch that polarization level, because it's a very small polarization signature. It's a purely geometric effect. It's not like magnetic field structure or something like that. So I think optical probably. So I think in fact, I may be wrong about the 4 meters. It might be a smaller instrument. I should look at that again. It might be a more reasonable telescope. So, but I think optical probably is the way to go.
Can I comment on that? The polarization is actually a combination of the magnetic field and the geometry. So if the magnetic field is entirely random, you will not see any polarization.
That's not true edge-on. When you go through the edge-on region, you actually see it just from a kind of, I think it's Sari, I'm trying to remember who wrote the paper. I don't have it at my fingertips, but even for a random polarization, you still kind of see things because you're looking at, it's kind of an aberration.
It depends what you mean by random. So
yeah,
you need to distinguish between random in the plane of the shock and random perpendicular to the shock. So if it's random in the plane of the shock, then you will get a very, very high polarization. You can get up to 60%.
Right,
50%.
but this is actually, yeah. Okay, but this is meant to be an aberration of a random distribution. But what you're saying, you raise a really good point, though. This is going to be buried also in any polarization signatures from the large scale, from the magnetic fields, so that it makes it doubly hard.
Yeah, and I think that the radio is also a good option for polarization measurement.
Yeah, but do you have to worry about self-absorption? Is it thin at that point? Or?
Well, maybe depends on the external density. In GW 170817, there was no the self-absorption was at much lower frequency. Typically, at this after weeks or 100 days, in the several gigahertz with typical densities, it's supposed to be the effect of the self-absorption is not expected to be important.
Paulo's point, I was just going to say that's a really good point. Radio is always better, right? On a new plot, it's better than everything. So self-absorption, that would be the point, Paulo. But what about, I mean, radio now can mean hundreds of gigahertz too. I mean, or
questions about gigahertz, then really it's not so important.
Yeah.
Yep.
Mm-hmm.
Jim, since you triggered this instrumental-oriented discussion, you mentioned about this Amigo, but and you said it's bigger. In which band you mean Amigo? For MEV part or?
I mean, yeah, MEV, and I just have to. As an experimentalist, we always want to pitch our own experiments. So I'm trying very hard to say that. But I have a funded balloon, an Antarctic balloon experiment, which is kind of a pathfinder. So
I was going to ask you. I was going to ask you, Jim. I saw your paper about 3 meter to 3 meter. Call it super.
Right. Oh, you did.
Super large
ICRC
instrument. Then why you didn't mention that? It should be more appropriate.
It's
an Amigo.
No, it's super cool because we're thinking of flying it at a Lagrange point. So we have top bottom symmetry. We're not obscured by the Earth. And because it's a multiple Compton instrument, you can see all the way out to almost 90 degrees. So you have 4 pi steradian MEV subdegree if we get something funded at the level of another Fermi funding level, which is a good fraction of $1 billion. So we're just trying to gradually build the case for such an instrument as a successor. And it also would be a pair telescope. So it's very much like, it's kind of like a super Amigo, but with very dumb, cheap technology and this multiple Compton. So that's my thought.
Jim, I think the multiple MEV Compton regime is getting more attention.
Yeah, attention.
I think that's true because it's been long neglected, and COMTEL, we've had nothing since COMTEL. It's been 30 years, and Fermi was very successful, but that's kind of like a missing gap. And there are many projects. I mean, yours, one of them, Amigo, of course. COSY just got funded.
COSY got funded, yeah.
Yeah, COSY just got funded. And we are also
good for gamma ray lines, right?
Gamma ray lines. And we at Columbia, we are also thinking of a GRANDS mission, which is the medium energy liquid argon time projection chamber.
Right.
So there's just so many of these.
No, that's why I don't want to mention my own. No, I just told you that.
But you should. You should mention, because I think that there are all of these different, I think it's important that, it just shows that there is an interest in the MEV region now, which is important.
And I just want to make it
limited.
Go ahead.
Sorry, Jim, interrupt.
No, you go ahead, Felix. I'm sorry.
I just want to say that unfortunately, in our yes, absolutely, MEV is an extremely exciting part, but whatever you do, sensitivity is quite limited, unfortunately. I mean, that was a bit. For LAT or super LAT, I mean, if you increase size factor of 10 area, then of course that could be kind of breakthrough even, but still, I think I just on the other hand, you have more fluxes at the MEV regions, so that is difficult to say. I just asked Jim because he didn't mention that. So in that case, I wanted to say that was my question was to Brian. that in fact the best GRB detectors now, not only GRB, we call now multi-dimensional, multi-messenger or whatever with gravitational waves, will be Cherenkov telescopes. I mean, if you manage to get 10 GeV or 20 GeV even dedicated to GRB detectors, and then the question is, the afterglows is fine, of course, but it would be nice to have also the main event. So there is probably there could be some hope that gravitational waves can trigger, and then it will appear before the main event. So just to observe them. What do you think?
That's why I think you have to pick which battle you want to fight when you design the instrument. So in the battle I wanted to fight was just a transient MEV instrument, not one that did a good job at background rejection.
Exactly.
It's big, all sky. And similarly for the GeV regime, I agree with you. You should not ignore the atmospheric Cherenkov telescopes, obviously, but the battle you want to fight again is near all sky sensitivity. I mean, I remember Bill Atwood even made this point at a workshop some years ago of what he would do next. So to me, that's the battle of space is all sky. And unfortunately, we've learned from Fermi, from like gamma ray burst observations in the LAT, we need more area too. We need sensitivity, and so we need instantaneous area. And okay, so to me, that drives the design. Okay, my goals are transients. Okay, but then if you want to do a good job on nuclear lines and so on, probably COSY wins, the day or something. I don't know.
Better probably separate tasks. I mean, to be
Yeah,
with instruments. I mean, otherwise,
exactly.
These compromises never work very well, actually. That, and then so if the another option is just the 100 GeV, which is this Hawk type, but if you go to 100 GeV like SWGO, and now Lhasa has 4 times more larger detectors than Hawk, and the threshold is 100 GeV, and that could be really very powerful. I mean, it depends. I mean, do you have 100 GeV gamma rays or not? At least at the early or afterglow or even main event, that would be great. Afterglow is guaranteed, but afterglow you can do Cherenkov telescopes perfectly. But for the main event or early afterglows, this we should not ignore also this low threshold, high altitude water Cherenkov detectors. And one is almost ready, actually. These Chinese Lhasa detectors, now they're operating, in full operation. The threshold is still, I don't remember exactly, 300 or 400, but this just artificially they put the higher threshold because they could not survive under the statistics. The detection rate, but it will be solved soon. So in that case, it could go, imagine, 4 times bigger than Lhasa Hawk and 100 GeV energy threshold. That could be another very powerful.
Sorry, Felix, on this front, how are they defining threshold energy here?
Sorry, Andrew.
What's their definition of threshold energy being used?
Well, I don't know what we use, frankly. But there are different definitions. The correct one, you multiply your correction area to different type of differential spectra, you see what is the peak. So that is effectively where you work. Some people use the half of the maximum, which is, I don't think is a good definition. But this 100 GeV, I think is quite, it's not terribly below nominal energy band. So I would guess that would be just like Hawk works at presently at 1 TeV.
It's not crazy for them to quote the half effective area kind of threshold, because this is going to be a super steep absorbed spectrum from a GRB, right? So it's going to, you know what I mean? It's, if you fold it with, you have to fold it with a very absorbed spectrum to say where you're sensitive. It reduces effective area, of course.
No,
So
this
the
is
question
right.
is, yeah.
Jim, they are not talking about, I'm talking about GRB at this moment. I mean,
Yeah.
just, we want to
They're
have
saying everything, yeah.
just like AGN or other things.
Yeah,
But
yeah.
so what comes to the GRBs, of course, I'd agree with you, but on the other hand, better to be open-minded, just not to
No, I think you're right. I think you're
steep.
No, I think you're totally right. And also they have an advantage for a GRB, it's a short transient. So they don't have to do a perfect, job with backgrounds and stuff, right?
Exactly. Yes, that is the point. So it's I just want to mention there's another potential instruments like this, like high altitude ones, and there are, I guess, I think it's against top, but people are talking about very low threshold Cherenkov telescope. By the way, Chinese could start this activity again, having this fast radio telescope, huge, that could be somehow. And then much larger lot, super lot, and that will be very difficult. What you are doing, I understand, and then Amigo, let's say, type, which is extremely important with all these caveats about the sensitivity, but probably. And it's
then
what is energy best?
Reshmi's argon TPCs are great for polarization and other things, so yeah, it's there. Yeah, you have to, that's why I say you have to choose the battle, like start with the science that you want to do and then think about the best instrument.